Dear students, in the last class we proved some results on cyclic groups and solve some problems. We end our last lecture with this example under addition modulo 4 Z4. This is from a find the generators of this is a cyclic group, and we find that show that 1 and 3 are the generators of this example. Now we have to continue this lecture with another example. Suppose consider we have to take a U30 under multiplication modulo 30, and clearly this is group of order 8. So we have to find the subgroup generated by 7. So we have to find the subgroup which is generated, because we have to prove the result that a group is if it's a cyclic group, then its subgroup is also is a cyclic. So if U30 is a cyclic, then we have to say that find the subgroup generated by 7. So let's start. We know that G is equal to G to the power n, where n is the element of Z. So we find a generator. So suppose 7 we generate, we have to find the subgroup generated by 7. So we start with the 7 to the power n is the element of a Z, 7 to the power 0, 7 to the power 1, 2 and so on, and then 7 to the power minus 1, 7 to the power minus 2 and so on. 7 to the power 0 is equal to 1, 7 to the power 1 is a 1, 7 square, 7 to the power minus 7 to the power inverse ka whole square and so on. If we have to take a 1, 7 square is equal to, we have to take a, because we have under the modulo 30, so we have a 19, and then we have a 17 to the power 3, we have a 13, and then we have a 7 to the power minus 1 is again 13, and then this is 13 square and so on. So we have a 1, 7, 19, 13, 13, and then 13 square we have a 9, next term is a 7, and we have a n is equal to 1. So generally we have to just 1, 7, 19, 13, and then we have to go to 13, 17, 19, 17, 7, 1, and then we have finally getting the all the elements. In this case is a 1, 7, 13 and 19. So this is the, if a subgroup is generated by 7 is the, this is clearly 1, 7, 13 and 19, and then we have to check under addition modulo 30, this is a form of group, and this is a clearly the cyclic group, because 7 is the generator of this group. So we can easily find in this way the subgroup of generating is a some particular elements of a group is there, group of the group element is there. Suppose we have to just Z under addition is a cyclic group, because 1 is the generator, then find generator of a 5, the cyclic subgroup of Z generated by 5. We have to generate it by 5. So we take a 5 can be written in the form of a 5, and n into 5, then 5 to the power n, then all multiples of a 5, n is a Z. So we can just write in the form of a 5 plus modulo Z is equal to n. So we have such that powers of all multiples of a 5, this is 5Z is equal to this thing. So if we have to find a generators generated by 5, all 5 into Z is a cyclic subgroup of a Z generated by this. If it's clearly this is we have a 5Z under addition is an abelian group, and this is this 5Z generator is equal to 5, and in this case we have a generator is equal to 1 is the generator of a this case is. So we can easily find the subgroup by the that theorem. If H can be written as generated by G, if G is a element of a group and G is a cyclic, then we can find it a subgroup which is also is a cycle. Whereas Z under addition, the cyclic subgroup generated by N, in general we can say that generated by N is NZ. We can find the subgroup generated by, for example, 3. So 3 is generated by 3 is equal to, you have all multiples of 3, and all multiple of 3 we can just say that in the form of this is equal to 3z, and similarly if you have generated by 7 is equal to 7z. So in this case we have to find, in this, if we have a z plus a cyclic group generated by n, that this is clearly is equal to nz. In general we can write z under addition cyclic group generated by the n element, n if generated by n is equal to nz. So if it is generated by 2, 2z, generated by 3, 3z, generated by 7, 7z, and generated by 11, 11z, like this. Now we come to the next part, how to find the order of a group element. We have to find the order of a group, means number of elements in a group is called the order of that group, and finite, if it is finite, is a finite, and if it is infinite, we can say that the order of a group is a infinite. If the finite number, so we have to, let us begin with the definition. Let G be a group and G is the element of a G. The order of a G is generally denoted OG, or we have to this by mod of a G. Is the smallest positive integer. This is clearly, we have to just say that. This means we can say that this one is smallest positive integer n, where is saying that when this g to the power n is equal to identity element. Okay? Means we find in a set the smallest positive integer when the power of a g is equal to identity, then this power is called the, if such n is exists, then g has a finite order. And the order of a g is what? That n is called the order of a g. If such n does not exist, so if no such n exists, then g has infinite order. Then the group, then the element of a g, we have a particular element, each element is, we have to find the order of this element. If such n is exist when g to the power n is equal to identity element, then that n is called is the order of this element, and if it is finite, is called as a finite order. If no such n exists in this case, we can say g has a infinite order. For example, identity of a group is the only element which has a order 1. If you take any identity element, you take a whatever this, you have to, for U7 for example, you can have 1 and 2, 3, 4, 5 and 6. So if you take a U7, then 1 to the power 1 is equal to 1, so order of 1 is clearly 1. So only identity element of a group is the only element having the order 1. So in the group, the identity elements, please take any identity element. If you take a set of integer under addition, and then you have know that the 0 plus minus 1 and so on, then order of a 1 is 0 to the power 1 means 0, so is giving the identity element. So clearly this is means order of this is equal to 1. So identity element of a group is the only element having the order 1. So for example, Z4 under addition modulo 4, so we take a element of a Z4 is equal to 0, 1, 2 and 3. We find the order of a 2. So we have find the order of a 2 means we have to take a 2 to the power 1 is equal to 2, 2 to the power 2 is equal to 2, addition modulo 4, 2 is equal to 0. So this is power 2 is giving this order of a 2 is equal to, we have a 2. And then for example, we have to find the order of a 3. So order of a 3 means 3 to the power 1 is equal to 3. 3 square is equal to, we have to take a 3. This means we can do 3, addition modulo 4, 3 is equal to, we have a 2. Again, not identity is not equal to identity here is equal to 0. So we can take another 3 to the power 3. We can write is equal to 3 square, addition modulo 4 is equal to 3. So 2 addition modulo 4, 3, 3 is equal to, we have a 1, again not identity element 0, then we take a 3 to the power 4 and then 3 to the power 3 addition modulo 4, 3. This can be written as a 1 addition modulo 4, 3 is equal to 0. So, we ultimately getting there that 3 to the power 4 is equal to identity element, then we order of a 3 is equal to, we have to say is equal to 4. So, clearly order of a 3 is equal to 4. So, we have a order is equal to 4 and order of a 3 is equal to this. Order of 1, if you find order of a 1, so we have to just take 1 to the power 1 is equal to 1 is square is equal to 1 modulo 4 is equal to 2, 1 की power 3 is equal to 1 addition modulo 4 1 plus is equal to 3, 1 की power 4 is equal to, you have 1 की power 3 addition modulo 4 1, so is equal to 3 addition modulo 4 1 is equal to, you have a 0. So, order of 1 is also, we have a 4. So, order of a 3 is equal to 4, order of a 2, order of a 0 is equal to, you know that is equal to, the identity element has a always is a order element as order of a 1. And now 1 is the, we have to take a set of all real number under multiplication and we can find the order of 1. So, this means order of under multiplication is identity is equal to 1. So, 1 to the power 1 is equal to 1, then 1 ka square is equal to 1 into 1 is equal to 1, 1 ki power 3 is equal to 1 into 1 into 1 is equal to 1 and so on, every time 1 ki power this. So, this means 1 has a order of is equal to 1, but 1 has a infinite order when 1 is equal to this thing. So, clearly we just say that if we have to take into this form, so 1 is equal to order of a 1 is equal to identity, clearly in this form we say that order of is, but if we take under addition, so identity in under addition is a identity element is equal to 0. So, you have a, if we have a identity element is equal to 0. So, 1 to the power 1 is equal to 1, 1 is square is equal to 1 plus 1 is equal to 2, 1 ki power 3 is equal to 1 plus 1 is equal to 3 and so on. If 1 ki power is not and, so this means 1 has a infinite order, we cannot getting identity of such a point. So, 1 has a identity element when 1 is the element of a R under addition. So, in the under real number under addition is a group. In this group 1 is the element which has order infinite, but if we take a under multiplication R star non-zero, all non-zero real numbers under multiplication is a group and 1 order of a 1 is equal to 1 because 1 is the identity in this case and identity element as a always is a order 1. Now, the order of any non-zero element in the Z under addition is infinite order. If we take a 1 is a order and here is also order of a 1 is equal to infinite, 1 to the power 1 is equal to 1, 1 to the power 2 is equal to 2 because 1 plus 1 is equal to 2 and so on there, no? Because identity element in this case is equal to 0. So, we cannot get identity. So, order of a 1 is equal to infinite, order of a 2 is equal to infinite, order 3 infinite, only order is finite is 0, identity element, that is a order is equal to 1 in this case. Now, we have to come to the form Klein's 4 group and then we have to show that clearly this group is not a cyclic and let Klein 4 group is we have to define as follows: G of is equal to E, A, B, C, where the condition A square, B square, C square is equal to identity and AB is equal to B. So, this is clearly is we have to show that because if it is not find any generator which can generate is there and clearly G is a abelian group. Further we have to AB square, if we take a AB square can be written AB into AB, we use the associativity. So, we just say that here now apply the commutativity because it is a abelian group. So, A square, B square and then you have A square, B square is equal to identity. So, if A and B are the element of this G, then order of AB is equal to, we have to say that is equal to 2. So, order of A is equal to, so order of A is equal to 2, order of B is equal to 2, and order of AB is also is equal to, we have to just say that is equal to 2. Order of identity is clearly is equal to 1, and since no elements of a G has a order 4. In this group we cannot find any, because this is order of this G is equal to 4, and we cannot find any element of this group which has a order 4, because order of A is equal to 2, order of a B is equal to 2, and then C is also order of a C is equal to 2. If we take A, C, B, C, so again order of A or B are 2, then order of A, B is also 2. So we cannot find any element which has a order 4. If it is not find any order group of order 4, then this cannot generate any element for whole this group. If it is not generate the whole group, then this group is not a cyclic group, we can say that. Let try the another example. We have to take the order of a, we have to show that order of a this is a element of a clearly GL2, because if we take this is a, so determinant of A clearly is not equal to 0. So this case we can say that simply is equal to, this is not a 0, so we have to show that this is identity. Let A is equal to this group, we have to just say that. So A is equal to this, then we have to take A square is equal to this, then this clearly is not equal to identity, because in this case the identity element is this identity matrix, and clearly this is the element of a GL2R. So this identity matrix, so if A is equal to this form, we take a square is the form of this, clearly this is not an identity element, so order of A this matrix is not 2, then we have to take a cube, and then I cube is equal to, you have a this, again this is the minus I, and clearly not equal to the identity matrix. So in this case also order of this is a to the power 3 is not identity. If we take a to the power 6, then we can take a to the power 3 to 3, then a to the power 3 ka square. So we just say that a to the power 6 can be written in the form of a this. So clearly we can say that if you take a square of a this, then you have a identity matrix. So you have a, if a to the power 6, clearly a to the power 6 we getting the 1 0 0 1, because we have to just say that this matrix, and this is clearly the identity matrix. So order of A is this matrix is equal to. Now we have to verify that, because we have to verify that order of a square is not equal to identity, a to the power 3 is not equal to identity. We also verify that a to the power 4 is also not equal to identity, a to the power 5 also not equal to identity. That means the smallest positive integer where we getting the identity element, this is the power is 6. So this is not identity, so we conclude that the order of this matrix A 1 minus 1 1 0 is 6. So this is clearly, this way we can find the this. Now we have to some properties of this order of a group. For any group element G, order of a G and order of a G inverse are the same. Order of a G and order of a G inverse are the same. You just see the previous examples, if you remember, here we just say that in this case we have to just take we have to this 1, and in this addition modulo 4, if you see addition modulo 4 1 0 1 2 3 0 1 2 3 0 1 2 3 1 2 3 2 3 0, then you have a 3 0 1, then you have a 0 1 2, and then you check we have to 3 and 1 are the inverse of each other. So this means the order of a 3 is equal to 4 and order of 1 is also 4, because we have to say that these two are the inverse of each other. So the first result is saying that if for any group element G, order of a G inverse is the same as the order of a G. Second result says that the order of any element of a finite group G is a finite. If we have a group of a G, then any element of this group G is always is a finite order. We cannot find a element which has a infinite order. So first we prove this. We have to prove that order of a G is the same as the order of a G inverse. So if order of a G G is equal to this, so we have an order of a G means is some power. So this means G to the power some k, and order of a G inverse means you have a G inverse to the power some k, and G inverse to the power k is equal to G to the power k ki power inverse, and then it follows that G inverse to the power k, because we can say the order of if order of a G is equal to k, then G to the power k is equal to identity. If G to the power k is equal to identity, so we have to show that because these are the same, so we can say that G to the inverse to the power k can be written as a G to the power k ka inverse, and G to the power k is equal to identity. So this means identity ka inverse is equal to identity. So in this case, G to the power inverse k is also identity. So G to the power k is equal to identity. So we can show that order of a G is equal to order of a G inverse. So if we take order of a G is equal to k, so G to the power k is equal to, we have a identity element. So G to the power k is identity, then we have to find the order of a G inverse. That means we have to show that G inverse to the power k is also identity. So we take a G inverse to the power k can be written as G k to the power inverse, and G to the power k is equal to identity. Identity ka inverse is equal to identity. So we have to easily prove that this means order of a G and order of a G inverse are the same. So both order of G and order of a G inverse are the same. Next we have to the next part is the order of any element of a finite group G is abelian. So now we have to show that if we order of any finite order of any element of a finite group G is finite. So we have to show that this complete by this, hence the smallest positive integer n is equal to identity. For the same smallest positive integer n, this is satisfied to this scope. Now with the second proof the part is. So second, for any for if G is the element of a G, if G is the element of a G means G is a, you have a if this G is a cyclic group, then there is a G can be written as a all the powers of a G square, Gn, because the G is a group, and by the group property this is a closed. If it is closed, then G square, G3, all the powers of a G are the element of a G. But because you have a group of order of a G is finite, so if order of a G is finite, that means it is all going to is not a distinct. At least some place they cannot of G cannot all distinct. That means somewhere we have to just take these two are the same. So there exists a positive integer R and S such that when GR is equal to GS. So all the powers we can, because the closure property G is the element of our G square can be written G into G is also belongs to that. Similarly, and because the group is giving is a finite, so this these powers of a G is terminated at some point is equal. So we have to we have to find a certain, there exists some positive integers R and S such that G to the power R is equal to G to the power S. If G to the power R is equal to G to the power S means if we take a G to the power S is also belongs to the G, this implies that G is a group. G to the power minus S is also belongs to the G because inverse property, so this can be G inverse to the power S is also belongs to the G. So G to the power inverse multiplied both sides by G to the power inverse, this means we can get G to the power R, G to the power G minus inverse, so G to the power S, G to the power minus S, this can be written as a is identity. So ultimately we get G to the power R minus S is equal to we have a identity element. So if it is identity element, that means we have to r and s are the positive integers, then is a we have to getting r minus s is also the positive integer, and then such that order of a g is equal to finite, we get a finite find a certain positive integer where power of a g is equal to, we have to giving the identity. So order of a g is clearly is a finite. So now I have remarked this. If it is very important to realize that if g to the power n is equal to identity for some n belongs to the n, we cannot conclude that the order of a g is equal to n, but only we have to just say that order of a g is less than equal to n, because we have to say that n is the smallest positive integer. We can say that if g to the power n is equal to this, so we only that order of a g should be less than or equal to n. So we cannot conclude that exactly this is equal to this. So I just prove this result for theorem where you say that let G be a group and G is the element of a G with finite order n, then if G to the power k is equal to identity if and only if n divides k, and if G to the power k is equal to G to the power r if and only if k congruent to r mod n, and order of a generator of a G is generated by E, G, G up to n minus 1, and the elements this all are distinct. So we just say that if generated by this, then all the elements of this are distinct. If G is a group and G is the element of a G, so with finite order n, so then we can prove that easily G to the power k is equal to identity if and only if n divides k, and G to the power k is equal to G to the power r if and only if k congruent to r mod n, and generated by G elements, all the elements of this are distinct. So let us prove the first one. We have to just say that we prove the result by using the law of exponents. So if G to the power k is equal to identity, then by the division algorithms we find Qs belong to the Z such that k can be written in the form of a Q n plus s, where s lies between 0 and n, and q to the power k is equal to identity. So g to the power k is equal to identity. So g to the power k can be written as g to the power q plus s. This can be written as g to the power qn plus s, and this can be written as g to the power q to the power n into g to the power s, and this means this is all the g to the power k. So then we have to just simplify this. The g to the power s can be written as a g to the power k, and this minus this. So g to the power k, g to the power n to the power minus k, and now g to the power k is equal to identity, and g to the power n because this is you have a given as a finite order is equal to g. So g to the power n is also identity. So identity to the power n is equal to identity. So we show that g to the power s is equal to identity, but if this s is strictly less than n, so this contradicts the minimality of n. Then this is only possibility is this s is equal to 0. So s is equal to 0. If s is equal to 0, then we have to k is equal to q by qn, then n should divide k. So by this we can easily prove that if we have a g to the power k is equal to identity, if and only if g is a finite order n, so we have a g to the power k identity if and only if n to the power k is equal to n plus this n should divides k. Now conversely, if n divides k, then k can be written as some n r for some r is the element of a z, and g to the power k is equal to g to the power n r, and g to the power n to the power r, and g to the power n is equal to, because finite group of order n, So g to the power n is identity, e to the power r is equal to identity, and then we have to say that g to the power k is also identity. So this first part is proved by trivially we can say that if g to the power k is equal to identity, then n should divides k. If n should divides k, then g to the power k is equal to identity. Now second part is if g to the power k is equal to g to the power r, if and only if g to the power k minus r is equal to identity. Now apply 1 and we get the required result, because if this is identity, then n should divide n minus k minus r, and if n this means this, if this, then by the first n should divide k minus r, and if this divides k minus r, we simply say that is equal to, satisfy this is equal to k is congruent to mod r mod of n. See, okay, this is clearly by the definition we have to result is getting to this one. Now clearly E, G, G, J, R is containing into the generated in G's, because we have to show that the equality is there. To prove the other inclusion, let S is the element of a generated by G. If X is generated by G, then X can be written as some powers of a G. So X is equal to G to the power K. For some K is the element of a Z. As a part 1, using the division algorithm, we can write K can be written in the form of a Qn plus R, where R is less than equal to 0 and equal to n minus 1. So X is equal to G to the power K, and G to the power K is equal to Qn plus R. G ki power Qn up to power is equal to R, and G to the power n is equal to identity. So we can say that e to the power Q, G to the power R, and that is equal to e to the power Q is again identity. So this is G to the power R, and G to the power R is the belongs to the we have a we have to just R lies between 0 to n minus 1. So this is belongs to E, G, G square, and we have to say that G to the power n minus 1. So if we write X is equal to this, then we have to just say that satisfy this generator is into this form. So this will show that generated G is containing into this form. So and hence G is equal to satisfy into this form. Finally, suppose G to the power K is equal to G to the power M, because we have to show that all are distinct. So we assuming that G to the power K is equal to G to the power M, where K is less than equal to M is or less than equal to n minus 1. So we just write G to the power M minus K is equal to identity, and M minus K lies between 0 to n. So we just say that this, which implies that M minus K is equal to 0, because n is the smallest positive power of a G, which is equal to identity. So hence all the elements of this are distinct. So this means we can simply say that all the elements of this are distinct. So clearly we have to prove the all three parts of this theorems. So clearly we complete this. So all the this means we can say that simply we can say that in this form. So this is trivially all the if G is a group, G is the element of a G with finite order, then if G to the power K identity, n should divides K. If n should divides K, then the order of a G is equal to K, and if K is congruent to mod R, then G order of a G is equal to same, and generated by G, and the elements of this all are distinct. So now I have to stop today's lectures here, and in the next class we have to continue some other some examples based on this theorem and some problems on the cyclic group. Thank you very much.